Okay, hello everyone. I'm very happy to have Saket Saurabh speaking. Actually, 1 minute. So is it okay to ask questions?
Yes. Yes.
I have one question. How come he has so many awards and honors? He has the ACM India Early Career Award. He has the Shanti Swarup Bhatnagar Award. He's a fellow of the Indian Academy of Sciences, a fellow of the European Academy of Theoretical Computer Science. He's a fellow of Academia Europaea. He is also a SwarnaJayanti fellow for Mathematical Sciences. And all of this is just the last 5 to 6 years. So you should tell us how that went by, and you should also tell us about the FPT Approximation.
That I will tell you after the talk. Okay. Thanks once for first of all inviting me. It's like I always wanted to come, but I didn't dare to come to TFR after my disaster tour in March 2004. Said, no, this is not the place I am going.
I have a question. What happened in March 2000?
That's not my PhD interview. No, it's not their fault. I remember very goodly that how bad I gave that interview, and I didn't feel like
I don't do that here anymore.
yeah, I didn't feel like showing my face to the people anymore. Yeah.
The question has nothing to do with the fact that Mank is an admissions coordinator for the last year.
Should I say the same if I come to IMSc?
You can. No, so this is like, so it was up and coming. So when Raghu asked me to give a talk, and he also preferred like Zoom over this, I said, no, this time I will make sure that I go in person, because I personally do not like Zoom meeting that much. At least giving talk, I find it boring. So I will try to tell you a little bit of story, not very deep as such, but like about a very new area, which is kind of merges, as I say. So the message is that very simple, that we want to develop algorithms that are like faster than what known FPT algorithms are, and approximation wise, they have better ratio than what is possible in quantum. So that is the very clear message. And the reason to choose this talk was also because many of you are here work in PCP or coding theory and this. And there are some very interesting questions that, according to me, are still up there. And a lot of people are, I mean, it's just that people like me do not have these tools to even attack these questions. So I will at least try to give you some glimpse of those questions. And then a little bit how we went about doing this algorithm. So, or as I said, like, why are we not able to do these two things? And what are the reasons behind the failure of designing good algorithm, which is kind of best of the both worlds? Okay, so this started when I was teaching in FPT Approximation course in 2001.
I don't know what FPT is.
I'll get it's like some buzzword for now. Okay. So I was teaching an FPT Approximation course because people were doing a lot of things. And this is where this started as a let's say, semester project kind of thing that we wanted to do. And we wanted to understand. So very soon we went out of what was known, and what we developed across like 2 years is what I'm going to give you some glimpses of that. Okay, so here's a maximum coverage problem, which we all have studied and seen in our basic algorithm course. You are given a universe of n elements and some n subset, and integer k, and you want to find k sets whose union is maximized. Right? So this is a very basic problem that we all have seen in some form or other. And what is set covered? You want to find minimum number of sets so that you are able to cover all the elements in the universe. So this is K version, and this is like when you want to cover all the elements. So these are the two problems that I will primarily focus on. And largely, this is what I will talk about in the talk today. So what is this greedy coverage of? Right? This is something which we learned, right? You pick the set that covers the maximum number of elements, mark elements in the chosen set as covered, and you repeat till you are done. So if you're doing for k sets, so if you stop after first k set, you get this 1 minus 1 by e approximation factor. And if you run until all elements are covered, you get this ln n factor for set cover. So these are the baseline of our algorithms that we will talk about. Okay, all good? Okay. So what do we know about these three problems in polynomial time? So unless P not equal to NP, you know that maximum coverage cannot be done better. So you cannot cover more than 1 minus 1 by E factor for maximum coverage. And similarly, it's known for, there is also a similar lower bound under P not equal to NP, but if you assume NP is not equal to polynomial, then you cannot do better than ln n factor for set coverage. Okay, so this is what we know in polynomial time hardness.
So NP not equal to P now.
But it's just that there's still, I don't know what is the
So subsequent to the notes to Euler,
Yeah.
assumption can be weakened to NP not equal to P.
Okay.
Yes.
Okay, so I'll just remove it.
It's the same assumption.
It's the same addition. Okay, so even better. Right? So this is what we know about hardness of these problems in polynomial time. That whatever greedy can do, we cannot do better than that in the polynomial time. Okay. So what do you mean by maximum coverage? So in parametric complexity, apart from the problems, we also have some integer parameters that we are giving, and we would like to have an algorithm with running time that governs these parameters. Okay. So for example, here in this problem, my K could be a potential parameter, right? Number of sets that you are going to use to cover as many elements as you need. Or the number of elements that you want to cover, or both of them. So like these are the potential parameters that one can come up with, and the objective will be to design an algorithm whose dependence on these parameters could be super exponential, double exponential, I do not care. But my dependence on U or M is going to be purely polynomial. Okay, so these are what we mean by FPT algorithm, which can be exponential in these parameters, but has to remain polynomial in the inputs. Okay, so these are the kind of algorithms we are going to make. So
there are chalks on the side if you want to use them.
yeah, so so this is what. So we are going to talk about these kind of algorithms. Or you can say T or whatever. Just okay. So, but it wouldn't matter anyway what the definition is, because every time I will write precisely what the running time of the corresponding algorithms will be. Okay, and set covered that is K sets such that its union covers the universe U, and here the K is used as a sort of parameter, the solution size. Okay, and what we know about these problems is that unless FPT equal to W1, meaning unless there is some complexity like P equal to NP, there's an analog in this world. If that does not happen, we do not expect an algorithm that runs in time f of K poly N and give you the best K sets that covers maximum number of elements. Okay. Similarly, say
K is the
number of sets.
N is the size of the universe.
Correct.
Okay.
Or let's say N is size of universe plus family.
Okay.
Okay. That is me. I should have written N plus N because number of sets could be arbitrarily large compared to N. So N, let's assume that N is whatever is given in your input, we are going to call it representative as N. Okay. And similarly, what is known for set cover, that you cannot have an algorithm of this kind for set cover. So these are no go in this world. So even if I give you so much power with respect to K, like double exponential, triple exponential, whatever, still you can't solve them exactly. Okay, so these are the basic hard problem in this area of parameterized complexity. Set cover is one basic hard problem. Click is another basic hard problem. Independent set is another basic hard problem on which the whole complexity theory is built. So assuming that these are hard, what else are hard problems?
Did you define what is W1?
No, I don't care. Because it's like I can define, but it is of no use.
So I can just read this as unless something.
Unless some unlikely collapse happens, we do not expect to have such. Like you can just like some, unless Earth collapses tomorrow, this doesn't. Okay.
Is there like a non-deterministic thing in the FPT world?
It's like some circuit. Okay. So like what kind of circuit we have, and 1, 2, 3, 4, 5 depends what is the number of large unbounded node in the circuit from top to bottom, like in any one. That's all it is.
So, and there could be algorithms which have FPT with respect to some parameters, but
Yes, but it may not have FPT with respect to this particular parameter.
Okay.
Yeah, this is always there.
Okay.
Right. For example, I can use input itself as a parameter.
Sure.
Right. Then every problem which is in NP is FPT with respect to that parameter, right? But generally, the most non-trivial parameter which has given much more results to the field is when you assume solution cycle. Somehow the dynamics of that parameter with input is much more complex as well as sometimes interesting than other parameters. Okay. For example, look at maximum coverage. If all I wanted that can you cover T elements, then I can come up with an algorithm which runs in time 2 to the power p of T. Right? So, and this is not trivial. This also requires something which you call color coding and this and that. But the moment I change my parameter from what was K, number of sets I needed, then I do not know how to design such an algorithm. But if I change my parameter to number of objects that I want to cover, then I'm able to design something. Notice that even with this parameter, you do not expect to have a polynomial time algorithm because that itself is polynomial. So overall, there has to have some dependence on these things, which doesn't look like polynomial if we believe in.
So now you have two parameters, K and T, and
That's
T is the parameters you have.
Right. That's okay. So what is an FPT approximation? So what we would like to do that the approximation hardness in P and exact hardness in FPT, and then it's a natural place to combine approximation and FPT, right? So this is what I'm going to show you, that maximum coverage via FPT approximation. What kind of questions we can ask for this in the world of FPT approximation, kind of answers we get, and how it has helped the field of FPT approximation to evolve by just asking this natural question about these two basic questions. Okay, so first question that people have asked, approximating the cover, right? So what I mean by approximating the cover, so like your universe U, family F, and integers K and T. So a factor alpha FPT approximation for maximum coverage will run in time some F alpha times K, and it returns one other thing. It says that there is no K size set that covers T elements, or I give you a solution set of size K that covers at least alpha T elements. Okay? Okay? And what is my parameter? Parameter is K. See, so I know that with K sets, I cannot solve it exactly, but maybe I can give you an approximation algorithm which covers 99%. So I'll give you K sets that covers 99%, or I will tell you there is no K set that covered T elements. So this algorithm can return you two answers: either that whatever you have given me is a no instance, or I give you a K set which covers almost as you want, right? And that is governed by this factor alpha, which comes in the parameter. Okay. And what is the, so now covered, right? So up until now, my approximation was with respect to how many elements I'm going to cover. But I might ask you that I want to cover all the T elements, but I allow you to take more sets than K. Okay. So this is what I mean by coverer. Okay. So what is this? Now I'm going to return that either UKT is a no instance, or I'm going to return a set of size beta K that covers at least T elements. So I'm not relaxing T, I'm relaxing K, like number of sets that you can pick up into a solution. In the previous question, I relaxed that you have to pick K sets, but I allow you to take less number of elements to be covered than K. Okay, so these are two basic differences between these two kinds of questions. And in classical setting, both have been studied and both have different approximation factors. So once we started to look into this, it made sense to look at both of these questions in the world of parameters.
So let's say alpha was the number less than 1, beta is the number greater than 1.
Yeah, some appropriate something. Okay,
So how should we think of parameter? Are these constants?
Constants. They're like some constant, or you can also look, depending on which problem you're talking about, they could also be a function of K. For example, look at click, for which in polynomial world, we do not know any non-trivial approximation. So if I say, hey, log K approximation in the FPT world, that will be great. Either I say that there is no click of size K, or I'm able to return your click of size at least K divided by log K, for example. Right? So depending on the context, the approximation factor can make sense from constant or some function of parameter or something, like again, it is completely context sensitive what you can define or what you can.
But in this particular context, that is in the maximum coverage, etc., because you're allowing for arbitrary functions on alpha and beta.
Right.
Alpha and beta are thought of as constant.
In this setting, it is completely constant.
Okay.
Yeah.
Also, so can alpha and beta appear in the exponent over there? Or-
Yeah, I allow it to.
I see. So they are not like KNT, they are actually.
Yeah. For a fixed constant.
No, we can
No, it is not a function of k and beta and k. There it can depend on whatever we like, but not in terms of n.
Oh, okay, so it's
N.
not the exponent.
No, it's not an exponent of n.
Okay.
It could be an exponent of
Yeah.
k and b. That's it. Okay. There are people who allow that, but then that leads to some different set of questions. But for this talk, we will avoid.
So, the question, you're integrating the size of the family.
Yes.
So which subsets from the universe can be allowed, or arbitrary subsets you allowed?
No, you're given a family as a part of input. No?
Right.
You're given a
So now you're going beta k of them. You're given k of them. but now
Yes.
You're going beta k.
yes.
So the family has four.
No, family has M.
So F doesn't have k sets.
No, as that n sets. You have to pick some k size subset of that which maximizes the number.
But it has to, so beta k has to be less than m.
Correct. I mean, if k is too large and beta k is more than n, then it's perfectly fine to return all the sets. That will be perfect.
Yes. Question.
Yes,
It would still be true that it's a low instance and you will return the stats.
it's possible, right? It's normal approximation of them, right? Sometimes sometimes there is a range in between where it could be no instance, yes instance, but you're still going to get some answer. So basically what happens that in classical optimization problem, the classical polynomial time world, we talk about optimization problem, right? Here I'm talking in terms of decision problem in some sense. So this is why it is slightly harder in some sense to keep in the head, but like it is on purpose because defining optimization problem in parameterized world is a mess. So then whole 1 hour of mine will go in defining that mess. So it's like, which I do not want to do. So like just much more easily, here are objects. Either you give me 2k size object that covers t elements or 1.5k sets that covers t elements. So this is the way to keep, or I'm telling you correctly that no way I can give you an answer because it's a no instance. Okay. 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 So what do we know about hardness in FPT? So he's passing, and he proved some very beautiful theorem assuming gap ETH. I will tell you in a minute what gap ETH is. What he said that you cannot do anything even if I give you not just FPT time, even if I allow this n plus n to have a function of little k, you cannot do anything better than 1 minus 1 little on general set coverage. So, like it's much more boosting of polynomial time hardness, of course, under much stronger assumptions like gap ETH. But this is what he managed to prove that if I give you a max coverage instance, hoping that you can beat this 1 minus 1 by e, even when I give you so much of computational power, it's not possible. Okay, so yeah, even in the problem is that there exist k sets that fully cover the whole universe, even then you can do it. So this kind of like a backbone where some of these things happen. And this came from people who were studying this approximation factor to beat for k median and k centered and k mean in FPT time. And they realized that they are able to beat, but it is more or less very closer to what they believe can be done in polynomial time, but we still do not know. Okay, so basically beating greedy is hard even in this world. And notice here, the kind of running time I was talking about, I was allowing the polynomial constant. Here, I'm allowing the limit of k. So this like number of sets that you're going to pick, I allow you to even choose k divided by log star k running time, and still you're not able to. Okay, so these are some of the results which were hanging around in the world of FPT. People were proving some of these things, especially Passin and some of other people have been the forefront of developing the lower bound theory of FPT approximation, which I'm going to tell you a little bit in the next few minutes.
So, quick question.
Yes.
So when is Parsons result from? This was
I think this is from 2019.
2009. No, because there've been a sequence of results trying to relate ETH
And come to it.
Okay.
Okay. Okay. So let's now that we have seen that here's the basic problem. This is how we can pose them into the world of FPT. So the first question was that can we do anything better? And here comes a negative result by passing that under gap ETH this is not possible. So people started to say, is the gap ETH is really the right assumption for the world of parameterized complexity? Because first non-trivial set of lower bounds that came in the world of FPT approximation were all via gap ETHs as early as 2017. Okay, so these are the hypothesis. What is gap ETHs? Gap ETHs basically says that you're given a 3-sat formula in 2 to the power little of n time, not 2 to the power n time, 2 to the power little of n time. I cannot distinguish whether this formula is fully satisfiable or almost satisfiable. Right? So this is what basically gap ETH means. And this is formulated by Dinur in one of our earlier paper, and then C defined it for different purpose, but then from that time it will become very standard to use in different contexts. Okay? So this is what gap ETH is, that in sub-exponential time, I cannot distinguish whether my 3-sat formula is fully satisfiable or almost satisfiable, and that almost is governed by this 1 million subset. Okay? There is slightly weaker assumption, which is ETH, which is much more believable, is there is no 2 to the power little of n time algorithm that can decide that given 3-sat formula is satisfiable. I don't care whether it is fully satisfiable or this. I just want to decide whether it is satisfiable or not. We do not expect to have 2 to the power little of n time algorithm. This is much more believable assumption because believing this, people were able to prove that most problems which are NP complete has similar kind of behavior. The way people believe P versus NP, that many problems have similar kind of behavior. So they showed, I think it was Paturi, Impagliazzo, and Zain, who showed that similar behavior is also possible for many NP hardware. So this is much more believable conjecture or hypothesis than gap ETH. So, but yes,
in gap ETH, what's the quantifier on epsilon? So is it that we believe there is a constant epsilon for which this is hard?
That's sufficient.
That's
Basically, you have a
sufficient.
PCP theorem. It will be implied in there's a PCP theorem in which the size of the reduction is linear.
Linear.
correct.
I see.
You have a
Okay.
Yeah.
Okay.
reduction in terms of linear time, then
Then
ETH will be implied by gap. Gap ETH will be implied by ETH.
if we had a linear size PCP.
Yeah. Okay. Correct.
Okay, but we wanted to have this in our own world of assumptions, like how, like whatever this means, that we have our own set of assumptions and we wanted all the hardness to have from our own set of assumptions. Okay, so we came up with this parameterized analog for PCP. We were doing something, we were designing algorithm, but our reduction had some gapness in the W1 hardness which we wanted to exploit. So we came up with this assumption or hypothesis in 2016, which says that there is some epsilon greater than 0 such that it is W1 hard distinguish the following fact. You are given a 2 CSP instance from K variables, and K is the parameter here, and alpha bit size N is completely satisfiable, or if every assignment to its variable satisfies at most 1 minus epsilon fraction of the constraints. Okay, so so notice that in n to the power k time, I can check because every variable can take one of the values in its alphabet, so which are n. So first variable has n choices, second variable has n choices. So in n to the power k time, I can check what is the total number of satisfying assignments. So what we said that in FPT time, I cannot distinguish that this formula, this CSP instance is fully satisfiable, or you have 1 minus epsilon fraction the constraints are satisfied. Okay, whatever this CSP is. So I just wanted to tell some of the experts here that this is what we came up with, and this somehow people picked it up. Okay, so we did not believe that people will pick it up, but somehow it has become, because assuming this, you are able to show much more hardness results for many more problems than this, and we ourselves will manage to show that gap ETS does imply this. So it is a weaker assumption than gap ETS. Okay, and recently, Guru Swami, Lin, Ben, Soon, and Bu have shown that in fact, you forget about gap ETS, ETH itself implies ETS. So if you believe, so basically they started with this 3-sat instance and created gap in that to come up to show that it is very recently it has been shown.
The best paper award and.
Yes.
Stuff, no?
Correct. So this is what it is. So all I'm saying to that, you start from this very basic problem and you start to dig deep, and it goes very deep. We still do not have PIH. Okay. So why did I bring this up? Because that this is interesting questions, right? Which I have no idea how they tackle it, but I don't know that much of what is that called coding theory to understand this gap implication well. Okay. But so another result that this is Bundelkhand, I think, and Karthik and Fasil, they overcame all this PIH and all this, and they directly showed very beautiful results for set cover or dominating set. What they showed that, assuming that W1 is not equal to FPT, there is no f of k FPT approximation for K dominating. You cannot come up with anything. Okay. Okay. And if you assume EATCS, they were able to show that you cannot have any decent approximation even in n to the power little of k time. And if you assume strong exponential time hypothesis, which basically says that if you have a SAT without 3 SAT, 4 SAT, the only known algorithm is to try all possible assignments to the variable, which is 2 power n. And we do not know how to design 1.999 to the power n. That is what SAT is. Then you cannot even have any kind of approximation in even k minus epsilon. They will also have some results from k same hypothesis and something. So all I'm trying to tell you that we came up with this so-called PCP version of PIH or PCP version for FPT world, but somehow the run time that is allowed in these reductions allows you to circumvent many more things, and people are able to directly show these kind of things. Okay. So
Go back to the PIH.
So
Even
for
I don't fully follow it. I don't understand what W1 hard.
So basically, you can give a reduction from click, which takes k to a function. That's all that we should do.
So the click size k is getting mapped to the number of variables.
Number of variables, and this k should be some function of k. That's just more than enough for you to understand what.
And otherwise, the reduction is the reduction should be n to the order 1 in the.
Correct. From 2 CSP to click is easy.
Okay. And when you came up with PIH, did you could reprove person's result with PIH?
No, because that came later.
So when you came up with PIH, what was the motivation? That is.
Oh, we were doing some directed odd cycle transversal,
Okay.
which people believe that it is W1 hard. FPT, we showed it is W1 hard. So we tried to come up with an approximation algorithm. We were able to give a factor 2 FPT approximation, and we wanted to know, does it have 1 plus epsilon approximation algorithm? Like, is it possible that we can go all like anything 1.00? And then we were not able to do it. So we somehow, these are the kind of problems which were coming in between. Then we were trying to formulate. So we just formulated that as our this thing. And starting from here, using all the known machinery from expander graph, we were able to show that there is some fixed epsilon that directed odd cycle transversal cannot have such approximation. So that was our motivation. Is that is 2 is what, or we can go down to some 1 plus epsilon. Okay. So it was more engineered from our algorithm than from the hardness perspective.
So on the face of it, this doesn't, I mean, okay, we were talking about the maximum coverage sort of problems.
Right.
And should I take it that for the coverage sort of questions, these are the hardness results that seem to be intimately connected to the FPT-ness of it?
Right.
Like, are there, like, for example, if you wanted to study a different question,
yes,
and you wanted to understand the approximation FPT world out there.
This is the basic question that helps you understand.
Oh, I see. So this is okay.
This is so like different people up until now have come up with some different hypotheses, like either gap ETH or this or that. But somehow this is able to give systematic answer to most of these questions. The way PCP gives a very systematic answer to most hardness of approximation. So like from here, at least you will be able to get for most problem some sort of FPT approximation. So in that sense, it has become a kind of people want to understand it best. Okay. But yes.
So there are these three sort of reductions. There is the standard NP not equal to P assumption to the PCP theorem. That's a reduction which is established and is
Correct.
serviceable. Now, based on this, you want to come up with two other reductions. One is ETH to gap ETH.
Correct.
That's this Pasin-Binur sort of stuff, which we don't yet know because we want the PCP reduction to be even better. We want to run in linear time and not just in polynomial time now.
Right.
So that's the ETH versus gap ETH.
Yeah.
Now, what you are now looking for is from FPT not equal to W1.
So some
want to get some.
Yes, some you start with some W1 hard problem or W1 complete problem, such as click or independent set, and give reduction to this. So starting from a non-gap click question, come up with a reduction that introduces gap.
So what goes wrong if you apply the usual PCP reduction on this? The parameter k gets
Like it just becomes a function of n.
It becomes a function of n.
That's where the problem.
That's where the problem.
So when you start to verify some of these things, like this 3-bit, those becomes k doesn't remains k, it becomes some function.
Okay, and FPT not equal to W1 to PIH is what you would have wanted.
Yes.
But what they proved is ETH to
this.
PIH, which is not the actual.
Which is not.
What you wanted. You would have wanted this.
Yes,
Yeah.
but still it is more or less.
Yeah.
Okay. Okay, so I've just advertised. Okay, but just few days back, like I think July 5th or July 6th, I found some very interesting results. Okay, which is, so I thought that now that these people know how to do set cover without PIH, right? They should be able to do for max coverage also, because it seems very natural that set cover and max coverage are interrelated problem. But what they show is that they gave a parameterized covering gap preserving reduction from max coverage to 2 CSP, which shows circumventing PIH seems difficult if you want to do for max coverage. So they give gap preserving reduction from max coverage to 2 CSP, to 2 CSP, right? So now these two problems are completely related to each other. So 2 CSP and max coverage are basically, now they have a gap. So we already knew a reduction from 2 CSP to max coverage.
Then you did you put the.
No, I didn't prove it, or did it? But that's very usual known reduction from what is that called? Old set covered P not equal to LP. That paper itself does.
So from PIH to.
Yes. Yeah. So that's your polynomial time what that reduction that itself works as a parameter reduction. But what was not known or we didn't believe is that from this to this, which these people are able to show. So it is passing, Karthik and me. So they recently came up with a reduction which shows that if you had a good approximation for max coverage, that would imply a good approximation for this and that. So now, like at least for this, now we need to prove PIH in its own glory. Okay, so that was all my what is that called? So this is the open problem here.
Once again, so now max coverage, you just need ETH for max coverage. That was already known before. That was followed from the Guruswami.
Okay, so
Sorry, what does circumvent PIH mean? I mean,
parameterized inapproximability hypothesis.
you mentioned what PIH means. What does circumvent PIH mean?
Like you don't need this hypothesis and you are directly able to show that you come up with a reduction from K clip, for example.
So when it is circumventing PIH seems difficult. I mean, this seems like a very strong result, right? It seems like
Yeah, it seems very like
all of these other techniques which are
yeah. So like now, like what I mean to say is that if someone is able to come up with a reduction or show the hardness for K coverage without PIH, it would also imply that we have proved PIH.
Basically, says you have to prove the gap version of the problem. You can't avoid it.
You can't avoid it. Okay. So that was, okay, now I will tell you something more lighter and simple. Okay, fun. Okay. So here, so this was for all the people who are doing PhD here, is that there are lots of interesting questions here, which is very related to the kind of things you will get to do. So we want to show PIH holds under this. Can we come up with a reduction from K clip, which gives gap for this? What is like this K clip, right? What do we know about K clip problem? So first of all, the only known well understood hardness was under gap mitigation. But over the last 5, 6, 7 years, people are able to show that you cannot have a constant factor approximation for click using not FPT not equal to W. But we cannot say that you cannot have little of log K approximation or little of K approximation, which you can say using gap ETH. That assuming gap ETH, in FPT time, you cannot even have little of K approximation for K click. But if I assume more believable hypothesis, then all I'm able to show is constant factor approximation, that you cannot have K by 5 or K by 10 click. Okay, so this still is very fertile and like people are trying to. So this is all the things which are, but we still, the point what Guru Swami said is that we need a PCP analog here so that we can explain all these things in a coherent manner. So up until now, most results are like just all across the place. Okay, so that is the bottom. Okay, I hope. Okay, so that was my detour to inapproximability. This is all that I know about inapproximability. So please ask.
So one quick question. So the PIH, the sort of CSPs that you work with, like are there situations where, for example, if the CSP, whatever the constraints that you have are of a specific type,
yes,
then that relates to problems of a specific nature or something?
Yes, we were able to show, like there's a version of monotone 2 CSPs in this, which we used, we were able to show them to be FPT, okay, and use those to design algorithms in computational geometry, for example. Okay, but I don't know from the hardness perspective. I like that you will have to ask other experts. So I have used more CSPs, like 2 CSP, special versions to design algorithms.
Okay.
Just in understanding the assumption, there's FPT not equal to W1,
Right.
There's ETH,
And then the gap.
there's gap ETH, there's PIH now.
Yes.
And ETH is sort of implying both, ETH is implying PIH. This is the
Yes.
direction you want. How do these two compare to each other, FPT not equal to W1 and ETH?
So ETS does imply FPT not equal to W.
ETH does imply
Yes.
this way. So,
So if you do, like, you can show very, like, you can show that you cannot have an FPT algorithm for K click, even f of K n to the power little of K, unless ETH fails. And that reduction is fairly simple. So after my talk, I can take.
but it's also conceivable that FPT not equal to W1 to PIH can sort of heard Venkat's talk for the ETH to PIH. This correct. It's a fairly involved reduction. This need not be that complicated, no? FPT not equal to W1 to PIH.
It may not be that complicated reduction.
Might not. So, but the point out there is you want to keep the parameter K to be
Some function.
some function of K. So K prime should be some f of K.
Some F. That's it. So that's the only constraint.
Whereas things could go polynomial and all it doesn't have to be a nearly linear time reduction.
Nothing. It could be FPT time reduction.
Okay.
Okay.
This, if I understand correctly, the FPT not equal to 1 is the strongest assumption.
No.
Weakest assumption.
ETH.
Weakest assumption. Sorry, it's the weakest assumption.
Okay.
Yeah.
And gap ETH
Is the strongest
assumption. Yeah.
Okay. Okay. So now it's time for some sorting. Okay. So
By the way, there is possibility that gap ETH might, because there's a recent result of Dor Minzer and others which says there's a PCP reduction that runs in n polylog n.
right.
Time and label cover. So it doesn't get linear, but can again. So it's
I don't know the future. I'm only telling you the snapshot. And that also I'm going out of my comfort zone to tell you this. I do not understand them fairly well. Last semester I tried to teach them so that I understand a little bit better. So now I have slightly better understanding how these reductions are happening. Okay. So my main message was that on general instances, allowing this kind of running time is useless for these two basic problems. That's it. Okay. So this is like one line message is that I picked up two basic problems. I showed you some, I expected that in this world, something interesting will happen. All I managed to do is to go around the world and say, hey, here's the question, does we have an answer? And then I got a bunch of answers from different people in different places. Okay. So that's it. Okay. So now I'm an algorithmist. I need to design algorithm for I need to eat some food, right? So here are some special instances, right? So there are 2-3 kinds of special instances people have considered in the literature. Each set is bounded. Okay, so this is called D set family. Each element appears in small number of sets. That is called frequency, right? Or universe family or incidence graph. I've defined what incidence graphs are. Like incidence graphs are basically one side you write elements, other side you write sets, and if an element appears in the set, you draw an edge. So this is the corresponding bipartite graph, right? Belong to some special graphs. Okay? And even these is quite fairly well studied. So for example, if each element appears in small number of set, even for frequency too. So if you have a set family where every element appears in at most 2 sets, then assuming UGC, you cannot do. So you know how to do 9.929, you don't know how to do 0.944. Correct. Right? So people have studied it in these special cases and to maximize. So we are talking about maximum coverage when the set family has a property that every element appears in at most 2 sets. Right? Not that set sizes are bounded or something. Then also we have such kind of things. And this is what I meant by incidence graph. You have sets in one side, you have elements in the other side. If an element appears in the set, I put an edge. Okay? So
Are either of those numbers nice numbers? 9.29.
oh, I don't know. I just copied it. Maybe there are some roots of something or something. That could be because it comes from some. I wouldn't be surprised if there are roots or something. No?
It's cos inverse of pi squared by 42.
Okay, it could be some of those things, but I. Okay. Okay, so I started to look at what happens if I look at this incidence graph and there's special plane, bounded degree, no variance graph, or whatnot you can think. So I wanted to come up with a definition which kind of captures first 2 things. Okay, so and this is how graph class inclusions are in general in the world of. Okay, so you have degeneracy, no variance, expansion, bi-click free. I will work with a graph which I am going to call bi-click free. What I mean by bi-click free, so if you look at the A and B, right, you do not contain a complete bipartite graph. I just subgraph or the use the button. Huh?
Green button, yeah.
The red button.
Yeah. Where do we take it up? Right, does it go to
Maybe on the other side.
You know, that one will know that one. The last one. The last one.
Okay. So this is my A. Okay. So when I say that graph excludes KDD, what I mean is that you cannot find D vertex here and a D vertex here and a complete bipartite. That's all. Right? Also, in the language, there are no D elements that occurs together in D sets. That is how I look at it. But the best is that you're given, I cannot find D vertices this side and D vertices this side, so that it could have edge. So this is what I mean by KDD, for instance. Okay, so now I can ask the question with respect to this incidence graph and say, you find K vertex in A, if I were talking about max coverage, you find K vertex in A whose neighborhood is at least. That's all. So you're given this bipartite graph, A and B, you're asking, can I find K vertex in A whose neighborhood is at least? Okay, and there is also notion of hitting set, right? What is hitting set? You are given sets and you want to find a subset of universe that intersects every element, right? Now, if I look at my look at this, then what I'm asking, does there exist K element in B side whose neighborhood is at least T? It means these K
B side were the elements, right? A is the sets.
A is sets and B sides are element, right? Okay. So let me just write it down so that it is right. Here sets, here elements, right? So if I wanted to hit T sets, then I'm trying to find K size subset in B whose neighborhood is at least, right? So if I move to this graph, both these questions becomes the same, right? Find a set whose neighborhood is as large as this. That's it. So that's an advantage of moving to this instance. And then it also gives us a simple problem, what is called partial vertex cover, which has been studied quite a lot in the literature, where each set in F has size 2. Okay, and then the parameters are again K and T. What do we know about this? Is that partial vertex cover, so we are given what? Imagine that we are given a graph and you want to find K vertices that covers at least T edges, right? So for that, you again have the same approximation factor. So you're fixing K, approximating the number of edges. People also have studied that you want to fix T, but you are trying to, approximate the number of elements that you're going to pick. And you have a factor 2 approximation, same like vertex cover, and you cannot have 2 minus epsilon approximation using UGC because it does generalize vertex cover. In the vertex cover, you want to find K vertices that covers all the edges. Here you are trying to find K vertices that covers at least the edges. Right? So for this also there is a factor 2 approximation and it is tighter than UGC. And surprisingly, if you wanted to find K vertices which covers at least T edges, I cannot design this kind of problem. For vertex cover, we were able, so this problem is, we can give a reduction from European set, which says that I cannot find K vertices that covers at least T edges. So this is the first problem for which people actually made some sort of FPT approximation long back, because it seems so much like vertex cover, which we all have killed to the death in parameterized complexes, right? With some 100 papers written on that to get the best bound in terms of how much. So currently the best running time for classical vertex cover is something like 1.25 or K. You see how fast it is.
I'm really confused. So vertex cover has an algorithm of
Yes.
that is FPT.
Now what you are asking? I give you K, I say, can you cover half the edges?
Right.
Right? With K vertices, can you at least cover half the edges? Then you're done. Right? So I'm not asking you to cover everything. I'm asking you, with K vertices, can you at least cover certain fraction of it? Okay, then the problem.
Definition of partial. That's exactly the definition of partial.
No, it's given T. You are given some number T, you want to cover at least K edges with K vertices. That's the definition.
And the parameters are both K and T.
Just K.
Just K.
With T, it's like, it's too big a parameter, you can show anything to be.
Okay.
At least
You know
that's
that
what
you need, if you want symmetry in the two sides, what is K here becomes T there, no?
No. Their T is number of edges. M.
Oh, N.
Right. M, number of edges. So if you want symmetry, okay, so K
K was the solution set on the A side.
it is either whatever, right? So it's B side because it's a vertex. Right? Because elements are here, so there are vertices and there are edges, two sides set, you put. So if you wanted to cover everything in A, right? I don't care about, then you have 2 to the power. This is the algorithm. If you wanted to find a K side set here for vertex cover, which covers everything, then you have such an algorithm. But if I say I'm not interested that you cover everything, but cover some T of them, then the problem. Right? So T is like A for vertex cover. Then, because then it's much more. Because for every vertex you have these 2. For every edge you look at 2 guides, you have to pick one of those guides, and that allows a good branch in the section. Now, this is how to do. Okay. And if you are really talking about number of edges, you can do all kinds. Okay. So, what was known for maximum coverage is that there exists an algorithm that if you give an epsilon greater than 0, it runs in this much amount of time and either returns that input is no instance or it will cover 1 minus epsilon times t elements. Okay. So, this is known result by, yeah, so this was known by, I think, forgot the name, SwarnaJayanti and someone. Okay, so this was known for the maximum coverage. I will show you one such algorithm in a minute. It was by SwarnaJayanti and Joeski. I cannot pronounce that better. They're both Polish. Okay, so for these kind of instances, you can have such an algorithm. And these are the kind of algorithm which we call FPT approximation scheme, because for any epsilon, I take more running time but I output you similar to approximation schemes, the problem called p-tasks or the VP-tasks. Okay.
It's an acronym for leading to all sorts of confusion. FP does.
Correct.
You should not be allowed to use that.
I agree. It's only later that I learned, and then it's like, oh, this is too much. I actually have got confused myself. And I paid for that. I saw that abstract and I agreed to review that paper. Think that this is what something about FPT approximation scheme. Then I opened the paper after I agreed. It was something very different. But no.
But an FPT is also, an FPT can sometimes be an FPT. Yes.
Right. So Mars gave the first FPT approximation scheme for partial vertex cover, and then lots and lots of people gave such an algorithm. Okay, and Manus, Rangi, and Skavern, and these people independently gave for partial vertex cover an algorithm with running time 1 by epsilon to the power k to the polynomial. So we can actually do. I mean, it's just hard. Okay, and these algorithms, they do not do it, but if you look deeper, they can generalize for even if you're doing for deheating sets. So
That's PVC.
huh?
You have FPTAS, you have PVC. You have marks.
Yeah, Marx is a name.
Name.
Marx is not an acronym. Not Karl Marx. And it's not Karl Marx.
You get no marks.
Okay, so let me not waste your time. I have one algorithm, right? Which is an easy algorithm. So let me. Okay. So what we were able to show is that if you're looking for this red-blue dominating set question, then you can come up with an S subset of A with this much time, and you can do 1 minus epsilon log. Okay, and what we were interestingly we were able to show that if you wanted to approximate number of elements, then you can show it to be FPT by just adding one extra element. So I'm either going to show to you that it's a no instance, or I'm going to find you a set A of size k plus 1, so the neighborhood is at least. Okay, so in that sense, we give additive approximation when you are trying to approximate the set. And I'll give you at least one simple algorithm for this. Okay, so if I specialize the partial vertex, or what I'm saying to you that either I will say it's no instance, or I will give you k plus 1 vertices that covers at least T edges. Okay? And at least this idea is very simple, which is the most natural idea that you apply. If you want to cover k things, cover many things, you sort the vertices by degree, and you hope that this will be a good greedy choice. So I sort the vertices in degree V1, degree V2, degree Vn, and if we first look at the k vertices and notice, what can you say? If you look at the k vertices, right? If I sum their degree, no k vertices can cover more than what these k vertices can cover, right? So, all, I think this is my inequalities are all wrong. No.
Seems right. Seems like a person with us.
Yeah. So what I mean, yeah. So this is looks. So if you look at summation of degree B, right? I think what I should have done in opt should be less than this. Opt is upper bounded matrix, right? Because you cannot with k vertices, you cannot cover more than what the top k vertices degrees can. Right? You cannot, like, look, now I'm just summing their degrees. The problem is when the reason the problem why this top k vertices does not provide you a solution because an edge is counted twice, one by this element, other by. If these k vertices were independent, then no k sets can cover more than these. Okay, so that was maybe there's some inequality here.
Maybe they are wasteful edges, like the top k are.
It could be a tree.
But they are.
Yeah, that's the only time that they are bad. Imagine that the top k vertices were independent set, right? But why top k vertices is not a good selection? Because of these k square edges. So they cover all but k square edges. Right? Okay, so this is what I mean. If you look here, imagine that k plus 1th vertex has high degree, 2k square, more than 2k square. Right? So you look at the top k vertex, how many edges did you sacrifice? K square edges? Next guy comes, he can only have degree to some at most k guy, and his degree is more than 2k square. And if I pick up these two k plus 1 guys, they have taken care of at least k.
Can we go with this argument?
Okay, so what I'm saying to you is the following. So look at the top k vertices. Top k vertices. How many edges you are counting towards? At most k square edges?
Yeah.
Correct. Okay. So your opt, your opt cannot be more than the total degree of these guys. Correct? Your k vertices cannot cover more than the total degree of the top k guys. And these k guys themselves are able to take care of everything but k square edges.
Yeah.
Right? So to take care of those k square edges, I'm including k plus 1 vertex. I said, hey, look at your degree. Your degree is 2k square. So you are only being sacrificed some k edges to the previous k vertices, but the rest you're giving me a new set of edges, which is more than what the top k vertices sacrifice. Right? So the top k vertices gives me all but say t minus k square edges. And for the remaining k square edges, I pick up my k plus 1 vertex. So that's the idea. So the reason why the top k vertices is bad, because there are a lot of edges among themselves, but that is not too much. That's just like k square, right? So if I can find an extra vertex from outside who can deliver me these things, then I'm very good. And that is what I'm doing. So, but the problem happens.
It's almost time.
Okay, so I'll take 2 minutes.
Yeah.
Okay. Okay. So there exists an optimal solution either from the top k guys or the total number of edges that you need to cover is bounded. Why? Because if you did not pick up the first top guy, then the k plus degree is small, right? So then I have a good branching strategy. Either I try this, or if t is more than this, then I know I need to pick one of these vertices, so I can branch into those cases. Or if t is small, then I can solve optimally by this 2 power big of t. Yes. I think at least I told you one algorithm. Okay. But this algorithm becomes difficult once you have a 3 hitting set or 4 hitting set, because now this idea that if you pick up the top k guys, number of edges that objects that they hit themselves is a function of k is no more true. So then you need to do much more fast. Okay, I think that's a good place to stop. At least I gave you one algorithm today. Okay.
Any questions?
Any questions?
Questions? Yeah, let's answer.
Now there is a question.
Yes. No, I just realized for this inequality, what has happened is that the opt k and the degree summation degree is gone. The summation degree for this is the opt is equal to zero.
Yeah. So this should have, this here should be.
Summation degree minus k square is less than equal to OPT is less than equal to summation degree.
Correct. Yeah, so that's first.
Minus k square plus k square. Does now PIH become the starting point of all hardness, population hardness reduction in the